So now as we get into lesson 4.3, we start using the derivatives of both the logarithmic and the exponential functions. So for instance here, and the reason why that these logarithms are actually used, and I think the other ones aren't even talked about, is that they're fairly simple. I mean, the derivative of the natural log of x is just 1 over x. That's all it is. So when you deal with circumstances, dealing with this derivative, such as this first example, say you were asked to differentiate f of x equals x cubed times the natural log of x. Well, obviously I'm going to have to use the product rule because, there's a product here. But as far as getting to the natural log of x portion of it, when I differentiate it, all I'm going to be doing is the natural log is doing 1 over x for that. Now, I still have to follow the product rule. So the product rule says that when I differentiate this, I'm going to do first 3x squared, which is derivative of the first, times the second, which is left alone. So 3x squared times the natural log of x, plus x cubed, which is the first left alone, times the derivative of the natural log of x. Now, obviously, here I have an x cubed times a 1 over x, which is basically dividing by an x. So I can simplify a bit further and say this is 3x squared natural log x plus x squared. And, again, sometimes simplifying does make things in the long run easier or more simple, hence the term simplifying, and sometimes it doesn't. I mean, you're going to see that we're going to be making use of some other rules of logarithms in particular when we start doing some derivatives of more complicated functions as we move along. But in the meantime, let's have you give this one a try. So for this one here, you're asked to find the derivative of f of x equaling the natural log of x divided by x squared. Now, you can use the quotient rule and do, bottom derivative top minus top derivative bottom all over bottom squared. Or you can, change this into x to the negative 2 power times the natural log of x as well. I'm going to work under both conditions. I'll kind of show how to do it with both situations. So if I just use the quotient rule, so leave it as it is, I would say that f prime of x equals bottom times the derivative of the top minus the top times the derivative of the bottom, which I'm going to put in front. That's usually how we write it. All over the bottom square, which is x to the fourth. With a little simplification, I would have x minus 2x natural log x here, all over x to the fourth. And I can actually, since everything here has a multiplication of x, I can actually cancel this, get a 1, cancel this, essentially get a 1. And cancel one of these to get a cubed power here. So I could have 1 minus 2 times the natural log of x all over x cubed. If I had chosen to do it the other way, putting in the multiplication first, f prime of x, I'm used to usually doing first derivative second, so I'm going to say x to the negative 2 times 1 over x plus the natural log of x times negative 2x to the negative 3. So with some simplifying, here I'm going to have, x to the negative 2 is 1 over x squared times 1 over x plus a negative 2 times the natural log of x all over x cubed. 1 over x squared times 1 over x becomes 1 over x cubed plus a negative 2 natural log x cubed. And of course, if I add those together, because they have common denominators already, I have 1 plus a negative 2 ln x, which is 1 minus 2 ln x. So as you can see, they're both the same answer. So it doesn't matter which way you do it, and that's kind of been the premise all along. So now moving on, they give you this additional rule of doing the natural log of some function of x. Well, it's just using the chain rule. They say here's a formula, it's f prime of x over f of x, but it's just the chain rule. You don't really have to memorize this secondary formula because it's the chain rule. But, so say for instance, if you're doing the natural log of x squared plus 1, the derivative of that would equal 2x, because that's the derivative of x squared plus 1, over the original function without the natural log, x squared plus 1. So they're saying that that's the way you could take on doing it. Meanwhile, I mean, if you didn't use that rule, you would just say, okay, well, if I'm doing this, I would do essentially, 1 over the x squared plus 1, because that's what we would do for a natural log, of a function, times the derivative of the x squared plus 1. You don't get much of a difference. I mean, they're kind of making it sound it's a new formula, but it's the chain rule. So whichever way you find it easier to remember. So it's not very difficult because, I mean, again, the derivative of natural log is not that hard to deal with. So so your turn. Tell me what the derivative of this function would be. For this one here, I do have an option, and I'm actually gonna take advantage of it because, I mean, I'd have to use the chain rule a couple of times because, I mean, I have a natural log of a quantity, but that natural log is of a quantity being squared, and I also have a quantity that has several terms in it. So I really don't want to have to go to, using the chain rule twice. So I can use the fact that f of x can also be written as 2 times the natural log of x to the fourth plus 1 because of a power rule for logarithms, which basically says if I'm taking the natural log or any logarithm of something raised to a power, I can just move that power in front and make it a multiplication. So now that squaring, which is a lot more complicated, leaving it squaring as far as the chain rule goes, is a lot easier now because I can now treat it as a constant multiple. So when I do f prime of x, the derivative, I'm going to keep this around 2 times 1 over whatever's inside the parentheses for the natural log, so that there, times the derivative of what's inside the parenthesis. Take that back. Got a little bit rambunctious there. Okay. 4x cubed. So if I put that all together, I'm going to have 8x cubed over x to the fourth plus 1. There's no more simplifying I can do because I do have 3 terms, 1 up here, 2, and 3. Not all of them have a multiple of x in them. The plus 1 in the third term, the second one on the bottom, doesn't have any additional x's that I can, factor out and, cancel out. So, I'm not. That's as far as I can go with this. Now, the derivative of e to the x, one of the simplest derivatives that you're going to ever have to deal with, because the derivative of e to the x is simply e to the x. Now here, I mean, I'm not going to go through every detail about this. Here's the explanation as to why. Because that's kind of why the function was kind of created and made. But basically, when you have when it reaches a value of 1, the exponential function, then the slope is 1, So essentially, it has itself as its own derivative. This is just a long explanation as to why it works that way. So say you wanted to find the derivative of e to the x divided by x. Again, I mean, this is a quotient rule. I could make it into a product rule if I want, but they're going to solve it using the quotient rule. All I have to do is just make sure I know the rule for differentiating e to the x when it's time for me to do the derivative. So if I'm going to use the quotient rule of this, I'm going to do bottom times the derivative of the top. So, that gives you that part there. Minus the top, which is the e to the x, times the derivative of the bottom. The derivative of x is just 1, all over the bottom squared. And I can simplify that a little bit more, get rid of some of the multiplication symbols, and just simply say that's x times e to the x minus e to the x. Sometimes they'll even take it a step further, and they'll factor it, and they'll say this is e to the x times x minus 1 all over x squared. It really depends on, who's writing the problem or something along those lines. But, neither one of them is particularly any easier should I have to do a second derivative. So it really doesn't matter if you choose to factor out the e to the x or not. So let's have you give it another try. Here's another function involving e to the x, and see what you can do to differentiate it. So the derivative of this, I'm going to obviously use the product rule. So as I said, I know it differently because I always do first derivative second, second derivative first. That's the way I've known it since I've been in high school. So if I do first, and if you want to take the extra step and write out, your intentions and say I'm going to do the derivative of the second plus the second times the derivative of the first. If you want to write this extra step out, you can. It does help you keep track to make sure that you've done what you need to do, because sometimes students will go through and write things, and then in the process of writing it out, they actually don't do a derivative. But for this, I'm going to have x cubed e to the x plus e to the x times 3x squared. So I can rewrite that as x cubed e to the x plus 3x squared e to the x. Oftentimes when you deal with exponential functions and do derivatives, you're usually going to be expanding it and creating more terms along the way, especially if there's multiplications and divisions going on. And the more derivatives you have to take, the longer the expression tends to get. So, those could be quite cumbersome after a while, and we sometimes do look for shortcuts to see if we can find a way of potentially making it a little easier on ourselves. But oftentimes you're not going to be able to simplify it so much that it's going to be like a really simple 1 or 2 step thing. You might have to do several derivatives along the way. So now again, for the exponential function, they kind of do the same thing they did for the logarithmic function and say, okay, if you're differentiating e to a function of x, but again, that's just a chain rule. I mean, I'm just going to treat the function itself as the variable, so I would just say it's e to that variable again, and I'm going to take the derivative of that variable. So again, they're taking a formula, they're making an extra formula here, which essentially is just the chain rule being applied to an exponential, where I'm doing an exponential raised to a function of x rather than just x itself. So, and a lot of it's just like kind of just copying the e to the x part, or the e to the f of x part. So if I'm doing the derivative of e to the x to the fourth plus 1, that's going to equal e to the x to the fourth plus 1, just copied. Now I'm just going to do the derivative of the exponent. So let's have u, and we could actually rewrite it a little bit. Um, oftentimes we tend to put anything in front of the exponential base e that's being multiplied to it to make it a little less confusing and less use of parentheses. So, and of course they also show you all this simplification of like this recap of these formulas. But as I said, these down here are just making use of the chain rule. I mean, so you don't actually have to memorize another rule for each one of them. It's just the chain rule applied to this circumstance. So, find the derivative of the natural log of 1 plus e to the x. So essentially here we're saying here we have a function f of x equaling the natural log of 1 plus e to the x power. So if I want to differentiate that, in this case here, the outermost function is the natural log. So when I do the derivative of that, I'm going to do 1 over 1 plus e to the x. They're kind of showing this, but I mean, I would just say I'm going to do 1 over 1 plus e to the x. And then I'm going to do, okay, working my way inside, do the derivative of 1 plus e to the x, which is 0 plus e to the x. So I end up with e to the x over 1 plus e to the x, which they're eventually going to get here. I mean, not to superimpose over it because there's more that's going to be coming. But, oh no, okay. So they just say, okay, one more step here, you work out the numerator a little bit, and there you go. I mean, again, it's just a chain rule. Again, don't get overwhelmed with it. Sometimes they put extra formulas here. I mean, but again, the chain rule. I mean, if I'm doing a derivative of some value k times x, I would apply the chain rule to it. So I would have to do, e to the kx power times the derivative of kx, which would just be k. I mean, so. Again, they're writing these as separate formulas, but it's the same general idea as the derivative of e to the x, except now we're applying the chain rule. So with these ideas in mind, show me how you would take the derivative of this function. Okay, so for this function here, again, when I do f prime of x, if I can get there we go, f prime of x, I have the natural log first, which basically means that when I do the derivative of the natural log of this whole quantity, I'm just going to do 1 over that whole quantity. And now I'm going to do the derivative of the quantity. And I'm going to break this down in several steps. It's not necessary once you get the hang of doing it, but, Well, as far as that goes, this is being left alone. When I do the derivative of this, well, when I do e to the x squared, I'm going to have to use the chain rule. So I'm going to have e to the x squared again times 2x, which is the derivative of x squared. And now I'm going to have minus the derivative of 2x, which is just 2. So I'm going to have 1 over e to the x squared minus 2x. Be sure that you're writing, exponents smaller, and make sure you're writing clear enough that you don't get them confused. Because the biggest thing that I've seen sometimes students do is that, as a side note here, sometimes starts becoming, which is not the same thing. Okay, so be careful. Just kind of get rid of that. Times 2x e to the x minus 2. And if I want to, I could rewrite that, and oftentimes the textbook will, so if you're checking your answers, you would have this over that. So this would be your final answer for the derivative of that function. Or at least one that the book would be most often to give you. So for this example here, putting it all together, so you may have multiple functions you have to deal with as you do these things. I mean, here I have a product involving an e to the x. I have a subtraction right there. I have a natural log function. And then I have a quantity raised to a power. So there's a few things I could do here. I mean, I could, if I want to, I could actually cube out the x squared plus 1 cubed, by foiling it 3 times. But that gets to make this even a longer expression. So I'm going to opt to use the chain rule when I get to that. So when I start doing the derivative of f of x here, f prime of x is going to equal first derivative second. And again, I'm writing more steps than I would normally write for myself, but I'm just trying to show like what we're working on. Plus second times the derivative of the first. This takes care of the product rule. Here I'm going to have minus 2 times 1 over x, as that's what the natural log of x's derivative is. 2 is just a constant multiple. Plus, when I do the derivative of this, I'm going to have 3 times x squared plus 1 to the second power times the derivative of x squared plus 1. So I kind of used this is where the chain rule might have been needed, or part of the product rule might have been needed. I wrote out that I'm going to do a derivative, but didn't do the derivative yet. So for this, the derivative of e to the x is just e to the x. So I'm going to have x squared e to the x here, plus e to the x here as well. The derivative of x squared is 2x. Minus 2 times 1 over x, I can actually write as 2 over x. Plus 3 times x squared plus 1 squared. And the derivative of x squared plus 1 is another 2x. So the last bit of simplifying I could do for this, or would need to do. This is all written the same up to here. I can multiply the 3 and the 2x and say plus 6x, x squared plus 1 squared. Now, if you FOILed things out or anything like that, that could certainly change some of how this problem goes. But, the answer shouldn't deviate too much from this. So let's have you do one. This one's not quite as bad, or as far as like the number of things that need to be done, but it does have its pitfalls. So have a look at it, give it a try, and we'll go over it shortly. So we have f of z equaling e to the z over 1 plus e to the z. So don't get too frazzled over the fact that they're using the z as a variable rather than x. So there isn't really any way to carry through any kind of division here that would make this any simpler. So I'm going to be using the quotient rule for derivatives here. So when I do f prime of z, I'm going to write out all the steps. I'm going to do bottom times the derivative of the top. This is going to be d dz of e to the z minus top times the derivative of the bottom all over the bottom squared. The top can be simplified a bit more. F prime of z is going to equal 1 plus e to the z times e to the z, because that's what the derivative of e to the z is, minus e to the z. The derivative of 1 plus e to the z, well, the derivative of 1 is 0. The derivative of e to the z is e to the z. As you can see, my 2's and z's look a lot alike, which is why I'm trying to write the z's to look like this. I usually put a little line through them, and the 2's that don't. So again, I could do some one little bit more of simplifying up there. I could distribute the e to the z in the first part of that difference, so I could have e to the z. E to the z times e to the z is e to the 2z. Minus e to the z times e to the z is another e to the 2z. And I can see I have a positive e to the 2z and a minus e to the 2z, so those would cancel. And my final answer would be e to the z over 1 plus e to the z squared. So basically the effect of the derivative on this function is that essentially all that happened is I squared the denominator. That's not to say that this is going to happen every time, so, and you're going to notice that sometimes when you have functions involving e, sometimes there's ways to simplify them to make them a lot easier before you go on and do any second derivatives or so forth. So, and that's always something I recommend that you do. So that's the end of this first part. Now I'm going to have you watch the second part dealing with examples 7 through 9, which you're going to try yourself first, and then I'll go over them. And then you should be ready to take on the problems from 4-3.